All right, section 1.8, optimization with linear programming. So I think this might be the first section where we've actually got something that isn't from Algebra 1, that you don't learn in Algebra 1. This is called linear programming, and that's just a fancy word for using inequalities, which we've been dealing with, to find the maximum or minimum solution in a given problem. Lots of these turn out to be word problems where they're applicable. So let's get started. What I want to introduce to you here is function notation, but using two variables. So we're used to like f of x equals 2x plus 1. You've seen that before. And so if you had that, so if you had f of x equals 2x plus 1, you don't need to write this down or anything. But if you had that and I said, well, what is f of 1? You would know that you take the 1 and you plug it in for x. So 2 times 1 plus 1 equals 3. So we'd say that f of 1 is equal to 3. So here we are going to introduce function notation in two variables. Let me show you how it works. So if I have a function that is f of x comma y equals 2x minus 7y, we want to evaluate that when x equals 2. We can do it. When x equals 2 and y equals 5. So it would look like this. F of 2 comma 5. That would be 2 times, and we're going to plug in 2 for x, so 2 times 2, minus 7 times, and we'll plug in 5 for y. And then for that answer, we will get negative 31. Okay, so function notation, plugging in an x and a y. Go ahead and try b on your own, and then I will show you how to do it. Pause it and try it, and I'll show you how to do it. All right, so hopefully you pause. Here we go. We want f of negative 2 comma 8. We will plug that in here. We will get negative 2 plus 7 times 8. That will give us 54. Okay, so how might this be applied in, in the real world, or in, in reality? Well, here's the situation. We have a dentist who makes $75 per cleaning and $45 per x-ray, and we want to know what is a function that will give you the amount the dentist earns with the combination of those two. Well, this is a perfect setup for a function that has two variables. So we'll write this, f of c comma x. That function will give us the amount of money made, and that will be $75 per cleaning, so 75x, or c, excuse me, 75c plus $45 per x-ray, so 45 x. All right, and so then we can use that in an actual problem. So the problem there, part D, says use the function from the previous example to determine how much money the dentist will make when she does 12 cleanings and 18 x-rays. Well, all of that is f of 12 comma 18. And so we will just plug that in. We'll get 75 times 12 plus 45 times 18. And when you compute that, you end up getting 17 tens, or $1,710 the dentist makes. Okay, now this is going to be applied, this type of function is going to be applied in the next example, where we're going to use, this is the actual linear programming piece of it, okay, is when we have constraints given by equations. So we have these things right here are called constraints, right? Given by equations, then what we'll do is we'll look at the graphs of all the constraints, and we'll get what's called a feasible region, okay, feasible region, and then we will find the maximum and minimum values of this function here based on the feasible region, okay? So now, there's a lot going on here. Let's try to break it down into small steps, okay? The first thing that we're going to do is graph these things. You want to write this down probably. These things here are constraints. Okay, this right here is our function, okay? So we will take our constraints and we're going to graph them, and then we are going to try to find the maximum and minimum values. But let's start with graphing, okay? So I've got this loaded up in Desmos already, and so we'll come over here, and I think I can put both of these on the screen. This first expression here, I'll have to turn the writing off in a second, but this first expression, 3 y is between 3 and 6. That's what that means. You would just graph, if you're using your graphing calculator, y equals 3, and you graph y equals 6. And it just means that it would be between those two lines. So you can see that over here. Those two lines are graphed here and here. It just means between those two lines. Okay. And then we also have this inequality. I've got that graphed, and then this one as well. And one thing I would say here is that you don't need the inequalities really, because you are just looking at this region that is on the inside of all of the lines. It's called the feasible region, okay? So you don't need the shading because honestly it can just make the graph look a little bit more cluttered, all right? So I'll come back over here, and so our equations right here give us this graph right here, okay? And I sort of wanted this the opposite side here, so okay, well I couldn't flip them around, so I guess it doesn't really matter that much. Let's take and analyze the feasible region. So this part inside, it's like a trapezoid here. That's our feasible region, okay, this inside part. And that's what you would sketch and shade. Now I'm not going to sketch it because it's right here. You guys can see the points if you want, but you might want to put a sketch of that in your notes, okay? So that is the feasible region right here. In a word problem, this will make a little bit more sense, but for right now, I know it's sort of annoying. It's like, what's going on here? But if given that feasible region, what we're trying to do is maximize or minimize this function in two variables here. Okay, so let's go through and do that right now. We have to be very careful when we do it. And the only points we need to check to figure out when that function is maximized or minimized is are the vertices. Okay, so we've got 4 vertices. We've got one here, 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 and here. That's all we need to check, and we're going to check it very carefully. Let me show you how. I would set up a table, and in that table, you're going to have x comma y. In other words, that's going to be your list of vertices. You will have the expression, which is 4x minus 2y. This is for the function. And then we will have the function value over here. Okay, so let's start filling things in. Our vertices were -2, 6, and 0, 6, and 1.5 comma 3, and -3, 3. All right, and we're going to plug those values into the function. And we're going to be sort of careful when we do it. I'll show you the first one here. Or I guess maybe I'll try and show you all of them here. That's going to get sort of cluttered, I worry. But all right, so 4 times -2 minus 2 times 6. Whatever that number is, that will be the function value. It turns out to be -20. And then I'm going to go 4 times 0 minus 2 times 6. That's going to turn out to be -12. And then I'm going to plug in 1.5, so 4 times 1.5 minus 2 times 3. That'll give you 0. And then 4 times -3 minus 2 times 3, that turns out to be -18. Okay, so there are all of our possible maximums or minimums. So you try and figure out which one is the max, which one is the min. Well, to figure that out, you just find the lowest and highest numbers. So here we have, this is the highest number. Okay, so that's going to be a max. That's a bad way to write that. Cresswell, bad. This will be a max. That's even not any better. This is a maximum, okay? And then where's the minimum? Well, that's the lowest number. Well, the lowest number is right here. -20 is the lowest number, so that will be a minimum. So for your final answer on this one, well, lots of times these questions will be asked. We'll ask you about each part individually, but your final answer here will be that you have a max at the point 1.5 comma 3. All right, and that you have a min at the point -2, 6. And what this means is that the function value, or the function in two variables right here, bounded by the feasible region, is maximized at 1.5 comma 3 and minimized at negative 2 comma 6. Again, these have applications to real world problems. That's when they're useful, and that's when what you did here can be applied in something that seems more in touch with reality. So that's it for section 8, linear programming.